Welcome back. We're going to move into our next video on our study of Unit 4, working on ways to think about multiplying and ways to think about dividing whole numbers. So with no further ado, let's get out to the share and load up this PowerPoint. Here we go. Slideshow from the current slide. There we go. You and I have studied exponents. You and I had an algebra point of view, certainly somewhere on our journey. So we're going to look at some properties for exponents that you might or might not remember from high school. We'll do a couple of examples whereby we will look at how exponents can be used to represent our thing. So if you've got a to the n, we probably do agree that that means you're going to multiply a bunch of a's together. And somebody says, well, how many of those a's? And the answer is n of them. So that's what you see there. All right, a to the n is a whole bunch of a's being multiplied together, where in fact there are n of those factors of a. All right, that was fun. Good stuff. A to the first is just a. You just have one factor of a. So in a sense, that's what you got. Nothing else to combine it with. All right, here come the properties that you may or may not remember. If you are asked to multiply two expressions that have the same base, all right, in this case, a to the m times a to the n, you keep the common base and you add the powers. So when you are multiplying expressions that have the same base, you and I get to add the powers. When you're multiplying something to a power to another power, powers to powers, if you will, we're going to multiply those exponents. In this case, we're going to get a to the m times n. If by chance we're asked to multiply several things to a power, what happens in effect is the power picks up each of those bases inside the set of parentheses. So we'll wind up having a to the n along with b to the n involved in our chain of multiplication. So anything inside the parenthesis is affected by the outside power. If by chance you're asked to divide and you've got a common base, in this case it's a, all right, what we wind up having done in the past was subtracting those powers. So in the case that you see here, we're going to presume that m is a larger number than n because we haven't done anything with negative powers. So we're probably not going to have that discussion in this class. So for right now, let's presume that the power on that top expression is either equal to or exceeds the power on the bottom of that expression. But in any case, when you're asked to divide, you simply subtract powers on the common base. Something to the zero power is a stickler. It's a pet peeve, I guess, that teachers, including me, have said anything to the zero power is one. And that's not true. It's almost true. So the way your author gets around it is he says, look, let's take zero completely out of the mix as a base, and let's decide that a has to be one of the natural numbers. And you'll notice that doesn't allow us to consider a to be zero. And then we can make the statement that 1 to the 0 or 2 to the 0 or 10 to the 0 is all worth 1. 0 to the 0, believe it or not, takes very strange properties. To do that idea justice, you need some calculus, and certainly you're not likely to throw that out to little Susie in second grade. So we will simply agree to say that as long as your base isn't 0, if you're raising that base to the 0 power, you get an answer of 1. All right, challenge for us now is to rewrite this thing so that we have one exponent. We currently, it looks like, have three different exponents. The 2 has a power of 8, the 8 has a power of 3, and the 16 has a power of 4. So you say, well, shoot, I got to get down to one exponent. This is going to be tedious. Well, what we're going to probably have to be able to do is rewrite the 8 so that it's a power of 2. And maybe if we're having a good day, we can rewrite the 16 so that it's also a power of 2. So, all right, sit and think about this for a second. I'm pretty sure I can convince you that 8 is 2 to the third. I'm pretty sure I can convince you that 16 is 2 to the fourth. So that's going to be our first step. We're going to change out the 8, we're going to change out the 16, and we're going to rewrite the 8 as 2 to the third. We're going to rewrite the 16 as 2 to the fourth. Now, in both of those right side expressions, please notice there's still an outside power. So we had 8 to the third, that's 2 to the third to the third. And we had 16 to the fourth, that's 2 to the fourth to the fourth. Powers to powers, we multiply. So the next step, you guessed it, we're going to pick up a 2 to the ninth. That's 3 times 3. Going to pick up a 2 to the 16th. That's 4 times 4. Now we have a lot of common bases. They're all 2s. And when we're being asked to multiply those guys together, we'll get the chance to add those powers. So we shall be done shortly. And all we have to do is add 8 and 9 and 16. And what, that's 33? Hey, my favorite number, 33. So 2 to the 33rd would be a correct response to that. I wouldn't expect you to write that as a number. We did exactly what we were asked to do. Found an answer with only one exponent. We'll play it again. Probably already know what's going to happen. We're going to try to rewrite. So you can see that 3 on the bottom. It's going to probably stay static. We could probably twist that 9 into a 3 to a power. And 36 is a little bit more problematic in that it's not 3 to a power, but it does have a factor of 3. So while we're thinking about things, let's go ahead and change the 9 to 3 squared. Let's go ahead and change the 36 to 9 times 4. Now that 9 that you see in there at 9 times 4 can also be rewritten so that it's 3 to a power. So let's go ahead and do that. We're not going to change the front action. We're never going to change the 3 to the 18 on the bottom. So what happened? The 9 became 3 squared, and the 4 became 2 to the second. All right, so there's a lot on that screen. Okay, so we're going to work on the top right, where we're going to take 3 to the second to the fourth. It's going to get us 3 to the eighth, multiplying those powers. 2 to the second to the fourth is going to get us 2 to the eighth. Again, multiplying those powers. And now what you see is we got a bunch of guys where the base is 3. So 3 to the 10th times 3 to the 8th should get us 3 to the 18th. Can't do much with the 2 to the 8th. It's just kind of dragging along. But we could now cancel the 3 to the 18th top and bottom. And we are left with what we were asked to do. Get an expression with only one exponent. This one, no doubt, I think for most kids was a harder challenge. It's good in that it gives us properties to practice with our exponents. Okay, base 10 blocks is going to make a big triumphant return, and we're going to showcase how we could show the kids what 13 times 5 looks like with base 10 blocks. So, okay, excuse the fact that they're different colors, but that's okay. In each row going across, I make the claim that you have 13. You have a stick of 10 and 3 ones. So that's 13. And you have 5 of such representations. You have 5 rows, if you will. So what you see in front of you is what it would mean to take 13 times 5. And you're sitting there saying, well, shoot, I know what we're going to do. We're going to trade some of those singles and try to get us another stick. So it looks like we certainly have well more than 10 of them. So we could grab 10. Now that's a lovely circle right there. We could grab those 10 singles and we could trade them and get another stick. So that's going to get us a bonus stick, baby. We'll have some singles left. It looks like 5 of them down there. But once we make the trade, we will now have 6 sticks of 10. So our answer for 13 times 5 by means of modeling with base 10 blocks will be 65. And again, not that it's that problematic for us to do this problem with the base 10 blocks, but for the kids who didn't understand the whole idea of why is there a carry? Well, that was the trade to get that extra 1 of the sticks. And we give the chance to do some of this with manipulatives on desks. We're going to set our kids up, I think, for better success on the multiplication algorithms that we're going to ask them to consider. Wasn't that fun? All right, you kind of already saw that. But again, what I want you to understand as a prospective elementary teacher is before we get into the algorithm and beat them over the head with, oh, geez, you got all this and you're messing it up. If we give them a chance to do it with the manipulatives, it'll make a smoother transition to what the algorithm asks of them. That, my friends, shuts down the video. We'll be back in a bit with video 4 for Unit 4. See you then.